Hello, everybody. Hopefully, everybody's having a good re:Invent so far. Awesome. I am Tyler Turk. I am an infrastructure engineer at Riot Games. I am a part of what's called the Riot Platform Group. We are a department that is responsible for all of the ecosystem around the game. So I don't get to do cool stuff like work on League of Legends or other products that we're building right now. But I'm on the team that's responsible for all player accounts, player account data, authentication, and authorization. You can see here, this is a picture of my family. I decided to include this here. I have an older daughter named Olivia, a middle daughter named Hadley, and a son who's named Hunter. I included this because it's incredibly important to me that when I'm not working, I am spending time with them and not responding to pager duty. It makes my family really happy that way, too. When I play League of Legends, I typically can be found in the jungle. That way I don't have to compete to finish last hitting the creeps there. So I typically play Nocturne, Kindred, or Kha'Zix. So I'm here today to talk to you a little bit about what we've done over the past 2 years or so. I'm going to start with a little bit of history of the League of Legends account service. Then I'm going to talk about what I think are some of the really important things when it comes to architecting a global service. After that, we're going to dive into how we've implemented the things that I think are important with building a global service. Some of the lessons that we've learned along the way, which there are a lot more than what I can fit into this 15-minute presentation, and end it with a recap. So, if you're not familiar with League of Legends, we are a massively online battle arena game. The company was founded in 2006, the game launched in 2009, and we grew incredibly rapidly. We partner with Tencent, who is our parent company, and Garena. Tencent runs all of League of Legends for China, and then Garena runs the Southeast Asia environments. Outside of those two environments, we run 12 League of Legends game shards. All of those player accounts were stored in 10 unique databases worldwide. Those 10 different databases stored hundreds of millions of player account records, and we performed over 1 million account lookups per minute. We handle several 100,000 authentication requests per minute, and we also have several 100,000 requests of people trying to break into other people's accounts. Because of this, it's incredibly important that we make sure that we keep players' data safe, intact, and secure. To do this, we have a couple different things that we've architected along the way, but I really want to drive home that a lot of our players feel really like their League of Legends account or their gaming account for any other gaming company is a core part of their identity because they've spent countless hours grinding and trying to get to the rank that they got. They may have purchased content in the game. So if they lose that, it's incredibly painful to them. So some of the early challenges, we have a lot of people in the community that like to joke about us being a small indie company, and that's why some things take a little while to build. But the reality is that we just grew incredibly rapidly, and there was a lot going on, a lot in flight all at once. We had several teams that started to build competing authentication and authorization standards, and different teams started to have different levels of dependency on these different solutions, which made it kind of difficult for us to align around how we were going to move forward. One of the downsides to rolling your own authentication and authorization platform is you might not be the foremost security expert, and you might take things for granted where you just think, oh, I did this thing and it seems smart, so it's got to be secure. But a lot of times you end up running into situations where there's just some small things that you missed. You also tend to have like a really narrow focus on this is the particular problem that I'm trying to solve. So I think that if I do it this way, everything will work great. Which results in you kind of having this really rigid kind of bespoke design that you have. Also, because of the way that we architected and implemented the legacy account service, we weren't able to integrate with third parties who would otherwise be able to provide our players a better experience. So if you play League and you're familiar with like op.gg, wouldn't it be amazing if you could actually log in with your League of Legends account and then have access to all of the player data instead of just the ranked data that we store publicly? I think things like that would make our accounts platform significantly better for all of our player base. So to accommodate for trying to do a little bit of a better job on handling all the authentication and authorization platforms that we had before, we built a system called Riot Sign-On. Riot Sign-On is built using OpenID Connect. If you're not familiar with OpenID Connect, it is a layer on top of OAuth 2. OAuth 2 is a fairly well-known standard. It's used by Facebook, Google, pretty much any big name out there that has the authentication and authorization platform that we're looking for. It's also provided by Amazon Cognito. So we built this to replace all of the legacy bespoke services that we had. And it was a pretty painful process, making sure that we had everything perfectly aligned with what other teams wanted, helping to make sure that this new service that we were building is something that would provide them the experience that they needed in order to support the players as well, and then get them to move off of the legacy services. This gave us the ability to adopt several security standards just kind of organically, given we adopted OpenID Connect. So here at the top, that little person is an imaginary player. This was what our service looked like about 2.5 years ago. The player would decide they want to log in. Their request would be sent to Cloudflare. We use the Orange Cloud DDoS mitigation. After you've gotten past the DDoS mitigation, we would send you to what's called our provider service. The provider is behind a load balancer. It would handle all of the general business logic around your authentication request. So if you had logged in before and you had metadata around your session, it would be routed over to the remember service, and then we could potentially restore your session. If your session was not remembered, we would also send you over to the velcause service. It's a velocity rate limiting service. So that is how we looked at the metadata on the request you were making and determined whether or not we should actually allow you through. Once you got past remember and velcause, we would send the request over to the auth service. The auth service is what actually does the back-end username and password validation. It's not on this slide, it's on the next slide, but we leverage, at the time, a distributed mesh VPN. It was not great. There were a lot of issues with network instability, random flaps. Things would just suddenly disappear and players wouldn't be able to authenticate. But there was a back-end service called GAS. GAS stands for the Global Authentication Service, which I think is really a horrible name because it was not global at all. So we took this, which was initially deployed in US East 1, and we decided to replicate that. So when we replicated that, this is a zoomed-in version of just 2 of our AWS regions. This is about what it looked like roughly 6 months ago. So from the internet, we then still hit Cloudflare. We do the Orange Cloud DDoS mitigation prevention. After that, we send you to a service called NS1. NS1 is a DNS provider that can do really cool things for your DNS, like do topologically closest routing, so that way wherever the DNS request is originating from, it'll actually sort the DNS responses based on whatever server that DNS request is originating from. And since Cloudflare has global points of presence, it makes it really easy for us to say, oh, you're coming in from Europe, we should route you to the Europe cluster. Once that's happened, and we've chosen the proper cluster for you, we send that traffic to our front-end router service. The router is a relatively simple service that just simply inspects your connection and validates whether or not you've actually authenticated against a prior cluster. The reason for this is, at this point in time, we did not have a global authorization store for all of our players. So if you authenticated, your authentication was actually pinned to a single AWS region. That's not a huge problem, but it still provides kind of a potential pain point for players in the event that an AWS region goes down. We would lose the ability for that player to still have that current login session. For the player, this doesn't represent very well because they're logged in, they're playing, they end their game, and all of a sudden they can't chat with anybody, and all of the other services that require authentication just didn't work. Pretty much everything else on this slide is the same as the last one. I realized there was one service that I left out kind of explaining on the last one. There's one here called C2ID. C2ID is a commercial off-the-shelf product called Connect2ID. It handles all of the OpenID Connect and OAuth 2 logic for us. The authentication service leveraged AWS Direct Connect. And here at Riot, we've built our own internet provider called Riot Direct. It's an incredibly amazing opportunity that we have this backbone internet provider that we're able to leverage. That ties into AWS via the AWS Direct Connect, as well as all of our physical data centers, which gives us really low latency access to all of the, I should say NGAS, because it's not the global authentication service, but gave us really fast access to that backend service to make sure that we could authenticate a player and then return the record. So I'm sure there's a number of folks here. Continue. There we go. The Global Data Protection Regulation, or GDPR. If you're not familiar with these letters, awesome, good for you, that's great. If you are, I'm very sorry. this is actually a really amazing set of laws that the whole purpose of that is to help provide better security for the personally identifiable information that you have and try and provide a better sense of security and ownership to the people whose data you have, which is critically important. For a lot of companies, they could see this as just a giant pain or something that was, you just have to do it because Europe says so. For us, we saw this as an amazing opportunity for us to prioritize a lot of the technical debt that had been bothering a number of us and very rapidly burn it down. It was an incredibly aggressive timeline, but we knew that we would have to modify the way that we stored players' data, and we would have to change the way that we thought about things. We also saw this as an opportunity to encrypt additional PII that doesn't necessarily need to be encrypted, but just helps provide that extra layer of security. We also had the discussion as to whether or not, because of the aggressive timeline, we should look at targeting this just for Europe, or if we should try and find a way to do it worldwide. And we chose the opportunity to work really hard together and do this worldwide. There were a lot of other features that we realized that we could really prioritize as a part of this. So one of those is called the globally unique player identifier, or what we call internally as a PUID. This PUID is basically a global representation of your account. It's a UUID that we have generated internally. The reason for this is prior to having this PUID identifier, you would need to know certain metadata about a player's account if you wanted to find them. The most important one was which game shard do they play on. If you don't know what game shard they play on, you have no idea how to look up that account. And if we need to look up that account, it just becomes incredibly complicated. On top of that, you also need some other identifiers, such as their account ID or their summoner name or something else that kind of ties all that together. So we saw this as an opportunity to build a truly global account lookup system. So that way, things that don't actually really matter to your game shard, like we have a merch store. If you wanted to buy merch off of our merch store, why do we care what game shard you play on, other than potentially your currency, which we could get off of other metadata, like your geolocation or the country that we have on file for you. It also gave us the ability to really think about how to architect this so we could have third-party support. So if you wanted to integrate with Twitch or OPGG or something like that, we would be able to start having that functionality. So as part of architecting a global service, there's a couple of key tenets that I think are particularly important. We wanted to have a situation where we had infrastructure that was repeatable. We wanted to make sure that this was something that was highly available, globally available, worldwide. I mentioned briefly earlier that Tencent runs our infrastructure in China, and then we have Garena that runs our infrastructure in Southeast Asia, which means we need to be really critical about the decisions and choices we're making for the infrastructure we're deploying. We also wanted to make sure that we have full data consistency. So if you're accessing any of your account data, we return the same password every time so you can log in every time. We want to make sure that if we're sending you emails, that it's using the correct email address. We need to make sure that all of that player data is exactly how you intend it. And then on top of that, we want a way to be able to verify that all of this makes sense, that it functions the way it's supposed to, it handles the amount of traffic that we intend, and that if something bad happens, we can easily recover from it. So from a repeatable infrastructure perspective, there's several different technologies that you could use. You could use CloudFormation if you're using just AWS. You could use Terraform. There's different configuration management tools, such as Ansible or Chef, that have their own vendor tie-ins, so you could leverage the APIs there for provisioning infrastructure. The key thing that we really wanted to make sure of was that whatever choice we made, it would be easily portable to wherever we needed to use it, and we would be able to have other teams re-leverage some of the things that we've already built so people aren't constantly reinventing the wheel. We wanted to be highly available. All of the blue sections that you see in this rotating globe right here are where we have a fairly high concentration of players. This means that it's really critical to us that we can provide a low latency access to your player account and to the game shards. We want to make sure that the material that we're showing you is relevant. For instance, in Korea, they have very different gaming laws than we do here. It's actually very serious. If there are certain actions that if we do not withhold, they will have the equivalent of a SWAT team actually raid the Korean office and take the head of the company there in Korea to jail. So it's incredibly important that we really think through how we do this, and we want to be fault tolerant and make sure that we can provide a good player experience everywhere. And the 4 hotspots you see here are where we have chosen to use AWS regions. We have AP Northeast 1, US East 1, US West 2, and EU Central 1. From a data consistency perspective, there's several different methodologies that you can leverage. You can look at using global rights with a multi-master setup. This is something that can be really great. For us, we thought it wasn't going to be the best idea because if someone modifies their account in one location and then another location, we have a split brain event, we need to know which of those account record updates we need to keep. How do we merge that data? There's also the possibility of a single right master with replication. For us, that works pretty well. Most of the time that you're accessing your player account, you're most likely just logging in or looking at some of the player account data. You're not changing your data super frequently, so if there's a little bit of an extra latency hit on the write that you're performing, it's not a big deal. Some other common strategies are federating or sharding your data. That one was really easy for us to mark off because that's where we were coming from with the prior global account service. And then finally, asking the question of whether or not you should or should not cache the information that you have. Caching was a pretty big pain point for us before, not really because the solutions we chose, just because we were bad at it, to be quite frank. When it comes to verifying the functionality of your service, there's several different things you want to keep in mind. One of the most important things you can do is have automated testing frameworks that not only validate the functionality of what you are building and verify that if I do these things, I get this output out, but also validating that what you think is the amount of traffic that you're expecting and the amount of throughput you're expecting, your service is actually capable of handling that. And then the final thing here on the slide is, if you're building a global service, having global tests is incredibly important. We could have just tested our US East 1 environment and said, yeah, it looks great. But without actually validating how everything works together and how all the pieces fit together, it's incredibly painful. If you play League of Legends, you might be familiar with this year in a review slide here. This was a pretty awesome feature that was built by some of the folks on our data team. And effectively what it did is it went through all of your League of Legends data for the prior year and then showed you all of the highlights from that year. So how many pentakills you got, how many different ranked games you got, what the highest point you were in the season, and just showed you all of these really amazing highlights. Our team had no idea that this service was going live. It was just another day, we're hanging out in the office, and we suddenly see over a 10x increase in login traffic. We panicked. We started looking for commonality in some of the locations that players were coming in from, and it was everywhere. We thought we were being hit by like the most distributed, crazy DDoS attack that we had ever seen before, and we started panicking. New Relic was going off, PagerDuty was going off. We had people jumping into our knock channel saying, hey, something amazing is happening, like all this traffic, we have no idea. And they're like, oh yeah, this team just launched the service. So had we known that in advance, we would have been able to go through and actually test and validate what that impact would have on us and better prepare for that. So it's really critical to not only test your service with what you think your throughput limitations are, but talk to other teams that could potentially be using the services that you build and validate what their expectations are as well. For last year, they changed it to where you didn't actually have to log in, and you could just look up your summoner name and get all of that data, which made it so much better. So, enter Atlas. As an aside, I really wanted to put my coworker's face up here because this is his baby. He started building it about 5 years ago. It got backburnered a lot. He told me no. So this is a complete overhaul of our sharded account system. This is the homogeneous blend of all of our prior player accounts, gives us a truly global account system. And the most important piece here is that it's completely decoupled from the game platform. The prior version, GAS, was actually co-located in each of the data centers with the game platform. In the event that we were doing a maintenance, it would be very common for our NOC folks to take the load balancer offline for GAS, which would then stop you from accessing non-game related services. So again, if you wanted to log into the merch store, or if you wanted to log into the forums or the boards, or just any service that leveraged your account, you wouldn't be able to. So it was really important for us to provide a way that we would be able to give that experience to players. And then it's not unknown. We're trying to become a multi-game company. Put that S in Riot Games. So in the future, ideally, our account system would not be tightly coupled with League of Legends, and we'd be able to provide that experience to players. So I've talked a little bit about what I think are some of the really important things when building a global service, and now I'm going to talk about how we've managed to implement a global service. When it comes to infrastructure management, we use Terraform, and the way we use Terraform is a little different from how a lot of folks probably do. We have this fairly large Ruby wrapper that I inherited. there is two primary components. We have what's called an environment. An environment in this Terraform setup is basically all of the ecosystem around EC2 servers. So if the service you're spinning up needs an S3 bucket, if it needs RDS, if it needs Elasticache, any of the security groups, we actually do include the Elastic Load Balancer in this. That's all controlled within that environment. We also then have deployers, which the deployer is a reference to the application. For most of the services we deploy, that is seen as two auto-scaling groups with two unique launch configurations. And then we have a manifest file that drives that with some metadata. So that way we can say we want to run this version of this application with this color. It's commonly referred to as blue-green deploys or red-black deploys. Just doing rolling deploys with two separate versions enables you to do a canary as well, so you can just roll one out and verify functionality. We do that for most of our applications. The latter half of this talk, I'm going to be focusing on a database solution that we've chosen to use. And for the database, we actually treat it much more like legacy data center infrastructure. We provide static instances. On these static instances, we give them a defined IP address when they start up. And then all of these servers, whether it be the static instances I just mentioned or our blue-green setup, we inject user data to that auto-scaling group or the EC2 instance directly for the static instances that defines some Docker Compose files as part of the upstart, so that way when the EC2 instance starts up, it will actually pull the Docker images that it needs, start up the service, and then register with a load balancer. Internally at Riot, we also have a global configuration service that's built on top of Eureka. It's effectively just a large key value store. We provide it what we call internally as an RFC 190 scope. It's basically a 5-component descriptive name that says this is for Riot regions, this is a production environment, and this is the team and the application that it runs for. Our team has built an additional service on top of this, so that way, instead of just a key value store, we can actually store arbitrary data types in there. So I mentioned briefly we use a couple commercial off-the-shelf products. A lot of times those are pretty hard to tie into whatever bespoke service you want. So we have a dynamic configuration tool that actually reads all that configuration data and then will generate templates based on that we define. And the Jinja templates store all of the configuration for what that service is expecting. We then have some startup scripts that will sit there and wait for a config manifest, and then once all the files exist, it starts up the service to avoid any race conditions. All of our servers are also fully Ansible automated. So we use the AWS Dynamic Inventory API, so that way we can tie into all of the different servers that we run. For most servers, it's basically just getting some stats and additional metrics that we don't have tied into other monitoring. But for the databases, it's actually critically important to how we manage and maintain those databases. I mentioned earlier that we're incredibly lucky and blessed to have this Riot Direct backend network. This is a snapshot of all of the dedicated lines that we've purchased. So the way this works, we have peered with different local internet providers, and using BGP routing, if you're accessing a League of Legends service, we will actually basically take control of your traffic earlier in the process, so that way we can make sure that you have a high-speed internet connection back to our services. This was really kicked off when different internet service providers started throttling game traffic without telling their consumers. We also use this to tie into each of the different AWS regions and our physical data centers to make sure that we have low latency access worldwide and that it's all over our own protected backend network. We leverage AWS Direct Connect for that. We use multiple lines so that way it's all tied in, and we have some fault tolerance if we need to do any maintenance and fully redundant links. That ties into the 4 different AWS regions that we have: AP Northeast 1, US East 1, US West 2, and EU Central 1. And then we provide low latency worldwide access using NS1. The NS1 setup uses a filter system. So we use the DNS name of auth.riotgames.com. That's sent to Cloudflare. We then do the Cloudflare DDoS mitigation, and then it's sent to a backend auth.riotgames.com endpoint that's only accessible via Cloudflare. And from there, we look at the topologically closest location to where that DNS lookup happened. We sort the results based on that. We then validate whether or not, according to what we have told NS1, that service is up. And then after that, we filter down the result to just one. We only ever want to route you to the closest cluster, so it doesn't really make sense for us to return all of them. In a future world, a really awesome filter that we'd like to add is something called shed load. I mentioned earlier that your authorization session is tied to the AWS region that you log into. So if we started shedding load, effectively you would just be sent to another cluster, and then the router service would route you back to the other cluster, which I don't think would probably make sense for us. For a consistency perspective, we use that front-end service router. The way it works is you authenticate your authentication. You get what we call a Riot sign-on token. Inside the Riot sign-on token, there's an access token and a refresh token. Your access token is self-signing, lasts for about 10 minutes. And the refresh token is what you use to actually get a new access token when that expires. We modify the refresh token to prepend a region code, and then we know which router to send you to in the event that you need to re-auth. We've actually piloted global DynamoDB tables when we set this up for our Garena partner. It seems to be working really well. So in the future, that's something that we hope to adopt for all of our Riot regions as well, so that way when you authenticate, we actually do have globally available authentication and authorization sessions for all of the players that access the service. That would then enable us to use that load shedding functionality. I mentioned briefly verification of load. This is a New Relic graph that shows one of our load tests after a lot of tuning back and forth. We use a load testing tool at Riot called Gatling. In Gatling, you define different Scala scenarios. Those scenarios should ideally map out to what your expected use case is. Before this, I did fairly extensive sysbench testing of our backend database. And we found out that all of the load that we were setting should be well within what we expected to send to these servers. I then spoke with some of our other application engineers, talked to them about doing some actual application load testing. They started building out some use case scenarios. They ran a load test. The database crashed. I thought I did sysbench pretty well, but it made me question myself a little bit. And we went back and I asked, did we double check the numbers? Are we sure this looks right? It seems high. I'm looking at these graphs, it seems high. And I got a very reassuring, oh, no, we did the napkin math, it's fine. So they ran the load test again, the database crashed. I went back and I said, please, let's do napkin math one more time. We found out we were sending about 2 orders of magnitude more write traffic than was intended. And after doing napkin math a third time, we were able to get this here where you can see relatively low database latency because it's accessing a local database, a little bit of time in the JVM, but all of these are responding in less than 20 milliseconds for doing player authentication, player account modifications, and player lookups. Once you have successful load testing, I'm a huge fan of chaos testing or fault injection testing. It's critically important, though, that when you're doing this, you do it after you have a successful load test, because if you do it beforehand, you don't know like if you're messing yourself up or your service can't handle the load. So some of the things that we did was randomly restarting different EC2 instances, intentionally killing MySQL processes, stopping services, starting services, restarting instances, adding and deleting network security group rules so that way we could simulate what a network failure would look like. Long term of this would be building solutions that actually tie into an automated ecosystem where you can have this validation done for you automatically. There are several companies out there that do this really well. Highly recommend looking into that if that's something you're interested in. Some of you might be sitting here wondering, well, this is cool, but why are you using MySQL? There's so many other technologies out there that would probably be better. Honestly, there's 2 main reasons. Reason number 1, there's a lot of people at Riot that use MySQL, so if I do something dumb, someone else could probably help me fix it. Number 2, we are owned by Tencent. Tencent is our parent company, and they have a very strong adoption and acceptance of using MySQL, so if we tried to force another technology on them, it would probably slow down the development, and then we'd have to fight to make sure that that is something that actually makes sense and not something that we're using just because it's the hot new technology. And finally, since we're storing player account records, having full ACID compliance, if you're not familiar with ACID compliance, that's having fully atomic operations, having consistency of your database, isolation of the database queries, and durability of transactions is incredibly important. I talked earlier about not wanting split brain events. If I have to manage those manually, that would be very painful, having to choose what player data to keep. So for our database solution, we chose to go with a third-party vendor service called Continuent database clustering. Continuent database clustering is made up of 3 primary constructs. The constructs, I'm going to start from the bottom and work my way up. The first is a replicator. The way the replicator works, MySQL is not actually configured for any replication at all. It doesn't know that it's clustered. It doesn't know that there's any other MySQL servers out there. It's just a standalone MySQL server. The replicator reads the MySQL binary log and converts it to what's called THL, or the transaction history log. This log is then flushed to the disk before it is then replicated to the other servers in the cluster. This is done intentionally to make sure that you have the durability that is provided by the binary log in THL. Once the primary server has replicated this over to the other two secondaries, these secondaries will receive that, add it to a queue, and then flush it to disk as well. So that way, if something happens in the middle of applying that transaction to the database, you have a point that you can recover from. The next component is the manager. The manager has two primary pieces. The first is being the cluster orchestrator and quorum manager. It uses JGroups behind the scenes to establish a quorum between all of the different managers that are running, get the general health and well-being of all those services, and then provides an API that gives you health and metadata about which server is the primary, which ones are secondaries, which ones are supposed to be doing replication. And then the second component is the wrapper service. The wrapper is literally just a wrapper around the manager that monitors the health and well-being of the managers so we can restart manager processes in the event that there's an issue. The final component is a connector. The connector talks to the manager API to determine which server it should route MySQL requests to. In the way that we have it set up, we have full control over our application, so we can use read and write splitting based on ports. So we send all write requests to port 3306, that's routed to the primary server. We send all reads to 3307, and that will be routed to whatever server is the most up-to-date with the write master. Once that's done, you're able to access all of the data however you need in any other region. There's one other way that the connector can be ran, and that is actually within inspection mode. We run it in what's called a bridge proxy mode. The inspection mode will actually analyze the MySQL query that you're sending to it, and then using JDBC, rebuild that query, potentially do optimizations, and then send it to the appropriate backend. That's really great for if you don't have control over doing read-write splitting, but we prefer the lower latency approach of being able to split it ourselves. I've spoken briefly about having 4 different AWS regions that we run this in. When we first started this project, US West 2 was the hub of all of the Riot Direct networks. So if we had traffic that was going from US West 2 to Europe or US East to Europe, both of those ended up actually routing back through US West 2. This made it really easy for us to decide to put the primary database source in US West 2 as its central hub. Then, the way the replicator works in this scenario, since we have 4 different AWS regions, you'll notice that there are 3 relays up there, one in each region that's not US West 2. It's basically a hierarchical model that the relay will talk to that primary server in US West 2. It will get all of the THL, make sure that it's properly added to the queue, flushed to disk, and then replicate it to the local secondaries that are there in that region. This provides us a global consistency model that doesn't add too much strain just to that one primary server, and make sure that we can replicate all of that data worldwide. We chose this instance type here. It's an R4 8x large, reason being it's a good amount of memory, relatively high CPU. Most important reason, 10 gigabit per second networking. We wanted to make sure that whenever players modified their accounts, we'd be able to really quickly replicate that over to another environment. We also knew that we had several hundred gigabytes of player data that we were going to have to migrate into this. So thinking forward, we wanted to make sure that when we imported all this data, we'd be able to make sure that it got everywhere quickly. We use a 5 terabyte SSD or GP2 EBS volume for the data volume. That is where all the MySQL data and the general Continuent tungsten clustering suite software goes. And then we have a 15 terabyte EBS volume that's leveraged for database backups, the THL logs, and the MySQL binary logs. We also have a couple additional helper scripts that we wrote. Since we treat this kind of like standard data center infrastructure, we know they have static IPs. We wrote some Apple OSA scripts, so that way we'd be able to just run some simple commands and SSH into all of them at once, do some triage if we needed. And we also have a good amount of Ansible automation that we've leveraged here. The Ansible automation that we use has 3 primary playbooks, and they all build off of each other. The first one is a general health check playbook, which is what you're seeing here. I wanted to do the other 2 ones, but they ran about 8 minutes, and I figured staring at one slide for 8 minutes might be a little long. So the health check logs into each of the database servers, hits the local API, takes all of that data and stores it in a dictionary in Ansible, and then validates that the health of the service looks good and is what it should be. And then as long as nothing fails, you'll see a bunch of skipped. That means we looked at the data, it says it's online, it says it's healthy, it looks good. The second playbook runs a rolling restart. I mentioned earlier that we use user data to inject Docker Compose files. We had decided that storing MySQL, the Tungsten clustering suite, our configuration, and our logging sidecars as Docker containers was going to be something that we wanted to do, so it would be consistent with everything else that we deployed. The way that that user data works is it writes into an upstart script if you're using Ubuntu. Upstart will only reload the configuration file if you completely stop the service and then start the service again, which means that we actually have to fully stop the Docker Compose, which means we're bringing down MySQL and the full clustering suite. Once we've done that, we can start it back up. So the first thing we do is we do this health check, and then if everything looks good, we go one server at a time, go through every server that's not the current primary, and then once we've done all of the other servers and we've restarted those services, we will then attach to the primary and then update, do what's called a cluster switch, and that will automatically elect a new primary server within the local service cluster. It takes about a minute for it to complete with a 12-node cluster that we have. So the way that works is it drains all of the existing MySQL connections, shuts down the service, shuts down the replicator, flushes everything, makes sure that there's another server that's completely up to date, promotes that to be the new primary, validates that all of the other servers in the cluster agree with that and establish that quorum. And then once that's done, bring that server back online as a secondary. That secondary is then restarted. The final playbook we have, I mentioned we use Docker. Since we use Docker, we can just update version numbers. We will update the upstart script behind the scenes to write a new Docker Compose file with the latest version of our Docker container. We also pre-pull that Docker container to make sure that we have the latest version that we're anticipating. And then we will do this rolling restart by starting all of that with the new servers. We knew that we needed to modify the way we stored our player data, and we needed a new schema. So as part of this, when we migrated from the legacy GAS databases to the new infrastructure, we copied all of that data into a temporary database where we were able to perform modifications of that data, and then we imported that into our database. We then wrote daily Delta update scripts, which would grab any record that had been modified within the past 24 hours, dump that into a MySQL file, and then import that into the destination database. We also knew that the database schema that we were going with wasn't going to be final. You'll notice I'm going to share a couple embarrassing stories. This one is definitely one of them. When we migrated from the legacy MySQL to the new MySQL, we had an ID column, and that was an auto increment ID. This auto increment ID was for the 10 disparate database clusters. So in the haste of making sure that we did this for GDPR, we introduced a primary underscore ID column. Now that might be a little confusing. If it's not, it was really confusing to us. We did one of the parts of GDPR is having the right to be forgotten, which means you can tell a company you have to delete my data. So we did that, and as part of that, we would mark accounts as ready to be forgotten, and we did MySQL queries using the ID column. And we had several engineers, myself included, look over this and say, yeah, it looks great. Right after executing the query, we started getting some notifications like, hey, we have players saying that they can no longer log into their account. It was great. So we had to go and look at prior audit logs to see which accounts were actually intended to be marked as forgotten, which ones we needed to restore back to prior service and make sure that we were able to get back to a known good state for all of those players. That being said, the schema is not final. We're not adding a primariest ID or anything crazy. I recommend really considering the schema that you're using, which this kind of leads us into why didn't we just restore from backups? So our initial backup process, I decided we have 4 different AWS regions. It would make sense to have a local backup. This is a lot of data. Every single AWS region can just perform their own backup and then push that to S3. If we need to restore, we can pull it locally. It'll be great. It was. The process started out. Basically, there was a cron job that would kick off. It would talk to the local API, determine which of the servers in that cluster were considered to be the coordinator, which is just a loose concept that says, like, I help make the quorum decisions within this local cluster. As long as it was the coordinator, it would then go through a backup server election process. This just looked like saying, are you a relay or are you the primary? If so, remove you. And then it would elect one of the other 2 that were a secondary in that local cluster to perform the backup. This would kick off the extra backup process, which takes all of the data from that data volume and moves it over to the logs volume. We would then compress that with something that's called pigs, which is just a parallel gzip. We told it to use 8 CPU cores. We had a ton of CPU available. We had a lot of RAM available. Everything looked fine. And then after the backup was encrypted or compressed, we would push it to S3. This process would take about 5 to 8 hours. We cut everything over. Everything looked great. It worked for several weeks. 2 weeks after doing this, however, we started having these really weird cluster flapping issues, and we had no idea what was going on. It would happen roughly at the same time every day, conveniently during the backup process, but not like right when the compression started, or when the compression was ending, or when we were copying files. It was some arbitrary amount of time that was kind of indeterminate after the backup started. We had several back and forth conversations with the vendor, trying to figure out if we were doing something wrong, if something changed, like why is this happening? We found out that one of the wrapper process around the manager was being starved for resources, which would result in it failing to communicate with the JVM manager. That manager process would then be seen as dead, it would be killed, and then restarted. That happening in rapid succession resulted in other ones saying, I'm seeing this really weird flapping. I think something might be wrong. I'm just going to go ahead and restart myself as well. Then we saw everything just start flapping. Sometimes this would recover, and everything would go back to normal after we panicked for a couple minutes. We'd dig through logs and see we don't really know what's going on. Other times, though, this would result in about 30 to 45 minutes where players were not able to modify their accounts, which to us was not acceptable. So the way that this kind of portrayed itself is we had fairly high disk I/O when we were copying from the data volume to the logs volume. Then we would see really high CPU utilization when doing the compression. And then we'd see really high network throughput when pushing to S3. None of those really seemed like they would have a big impact on the service, which you can see on this slide. We only got to about 35% CPU utilization, which means there's a lot of room. So to make this better, we decided to just do a backup in a single region. We chose the cluster that's getting the least amount of traffic right now. That's our US East 1 cluster. We would do the backup on that location. Everything was fine. Every now and then, one of the manager services might restart, but all of the other backend services continue to function, and it's still seen as an eligible member in that cluster. And then when it comes back online, everything is in a known good state. The long term, which we're in the middle of right now, is adding a standalone tungsten replicator service. This is effectively another server that you just dangle off of the database cluster, and it has no impact on the cluster whatsoever. It just is set up as another replicator that pulls that data to itself and doesn't receive any of the database queries. One of the other really nice things about this is you can actually set up intentional delays. We're planning on probably putting in about an hour delay, so that way if we do a little mess up again around primary ID versus ID, we can just go back and look at what the data was an hour ago instead of having to cull through several event logs and trying to figure out what needs to be rectified. And this here is a graph showing the backup in US East 1 where you can see the elevated CPU, the elevated disk read and write IOPS as it's moving from one EBS volume to another, and then the elevated network throughput. Along the way, we hit a lot of bumps, and we learned a lot of things. One of the first things was that the monitoring that was provided by the vendor tied into several different services, but nothing that we used. So we needed to build something that would tie into our monitoring service and be able to provide us visibility into what we wanted to do. I mentioned earlier how we would remove servers for, oh, actually, I didn't mention this. One of the other features that we have is we can do online schema migrations with this database cluster. The way that works is we pull one server out of the rotation that is not a primary. We tell the replicator to go offline, and then after we've shut off the replicator, we can do a schema upgrade on that because we just do a MySQL query to add an index or modify a column. The most important thing is that this modification has to be backwards compatible. Once we've done it on that server, we can bring it online, add it back to the cluster, go through the remaining servers up until you hit the primary server, and then you do the same cluster switch I mentioned earlier, which promotes a new primary, and then you will do the schema migration on whatever the primary or the former primary was, so that way you have a consistent world where all of them are up to date. We've done this a couple times. This is actually, the bottom 3 shows the approximate latency. This is after we did a massive modification of the schema, and you can see the cluster catching back up with replication after we brought that server back in. The center row there shows a little bit of information about what level of traffic we're seeing on the database, the approximate increase in writes, and the number of connections to that database. We also have some general monitoring around the state of the cluster, showing the health of the manager service, whether or not the data server is online and the replicator is online. There's also several different pros and cons of containerizing your database. One of the great things is that it kind of gives you this immutable infrastructure. So you have this idea of, I built this exact artifact. This is the artifact that's deployed. We're relatively close to that with the exception of our dynamic configuration service. That dynamic configuration service renders a configuration template and puts it inside that container. So from that perspective, that is dynamic and will change, so it's not fully immutable. Another potential pro is that if we decided to, we would be able to take this and push it into a portable scheduled environment, such as Mesos or Kubernetes or ECS, EKS, et cetera. One of the downsides that I mentioned briefly is that doing these types of database modifications or rolling restarts, by having it containerized, it requires a full restart of that database, which does result in impact to players, which is not ideal for us. From a design perspective, one of the most important things for a global service that you can do is kind of document and draw your design and implementation and communicate that with other engineers. By writing this down and providing actual documentation and images of what you're trying to achieve, you set yourself up in a situation where people can actually see and understand what you're intending to do, and you'll a lot of times find potential flaws that you would have otherwise not noticed. But on those lines, avoid the ivory tower approach. If you're not familiar with the ivory tower approach, it's where you sit down and you build this design and you keep iterating on it and iterating on it and you try and come up with what the perfect thing is. The most important thing you can do is align around a concept and then just do it. If you wait and try and find the perfect design, you're going to find yourself in a situation where what you build might not actually be what you're trying to get for whatever it is, your players or whoever's going to be leveraging your service. When building your VPC, please consider your subnets carefully. Don't do what I did. I was asked to set up another VPC when we were initially standing all of this environment up. I made the subnets way too small, and then we ran out of IP space, which is incredibly painful. Moving subnets around is difficult. You have to shut everything down in it, delete everything in it, free up all of those IPs, delete the subnet, and then recreate it. So really, when you're doing your design and your documentation, if you are building a new VPC, consider what you're doing. In some cases, it might make sense to have per application or per instance type security groups and subnets. This allows you to, if you have cross-regional things, just whitelist those. If you only have 2 AWS regions, you can use VPC peering, and that way you can actually cross-reference the security groups in different regions. Otherwise, if it's all on backend IP space, having a subnet that has a defined IP makes it a little bit easier to whitelist across subnets. Along those same lines, evaluate the security group and networking constraints that you're going to have. We run this in 4 different regions using Direct Connect. All of that is over a 10/8 network. This enables us to whitelist different IPs, but since we don't have per application security groups, we have to come up with crafty ways to make sure that what we're whitelisting across those regions is actually what needs to be whitelisted. When building services, understanding what it's actually doing is critically important. It works well for your auto-scaling groups and making sure that you understand what's happening with the application. For instance, if the bottleneck of your service is backend database connections, spinning up more servers is going to give you a really bad time. Don't do that. Make sure you understand what those limitations are. Is it network? Is it CPU? Is it RAM? Right-size your instances. That's going to save you so much money. When load testing, please, it'll make your infrastructure engineer happy. Double and triple check your load test numbers. Make sure that what you're sending is actually what you intend. Along those same lines, map out the actual use case for what you're going to be testing. Make sure that you replicate the expected traffic patterns and you have a good understanding of what it is you're doing. This isn't always easy. Sometimes you don't know what the usage pattern is going to look like. In that scenario, just do your best. Along those same lines, understand the data access patterns of your application. For us, we're really read heavy, so having a single write server in one region made a lot of sense for us. It might not make sense for you. Make sure you understand what you're doing. Leverage servers where possible. I am not a DBA. I am not excited about being a DBA. I am currently a DBA. If you can leverage a service, use it if you can. If you don't have those resources where people actually understand the backend service, you might become a single point of contact where you're the one that gets paged whenever it goes down. I know it was like that when the backup stuff was happening. There were several mornings we got up at 5, then we pushed the backups back 2 hours so I could wake up at 8 instead, and then we figured out the problem and we fixed it. Along the lines of making sure that you understand how to run your service, when doing WAN replication, it's incredibly fragile. Even if you run your own network, there's going to be things that cause interrupts. There's going to be things that cause data segmentation where you need to be able to recover from those. In the instance of using services, just make sure you have valid monitoring that shows you whether or not your service is healthy. So to recap, when you're designing and implementing a global service, make sure you thoroughly consider the goal. Make sure that you think through your design, you write it down and you share it with people, and you get feedback. After that, make sure you iterate and you test the infrastructure that you're building to make sure that you're doing what you set out to do. By doing this, you'll set yourself up for success, sometimes failure. I'd like to end it with this quote. Failure is simply the opportunity to begin again, this time more intelligently. I've shared multiple times that we have failed. I will continue to fail. Don't be afraid to fail. It's what makes you better. You can stand up, do it again, make sure that what you're building is what you intend, and then get to a point where you have solid infrastructure. I'd like to thank you all for the time. After this, I will be in the speaker Q&A lounge, and they asked me to make sure I include this. Please complete the session survey in the mobile app. Thank you very much.